for this special opportunity for a three-way talk. And well, and so first I will start with the introduction. Basically, I will tell you about what we've been doing at the with the H1 emission measurement at the epoch of realization and also at low redshift. And so this is obviously not lensing, but I'm hoping this would be an introduction for Tingting's talk, and for Weily's talk, where Tingting will talk about lensing with 21 centimeter, and Weili will talk about the saturation effect. And this, of which the work where Olivia is also involved in. So just a very quick, a simple introduction for 21 centimeter. As you know, it is the hyperfine transition of the hydrogen line, and it is optically thin, so it is in principle visible throughout the universe after the spin temperature decouples from the CMB temperature. And so we are focusing in a regime where the spin temperature is much greater than the CMB temperature. So we should be able to see H1 in emission after redshift 10-ish. So there are two types of cosmology that we would like to discuss here. So so there are two redshift windows. At high redshift, redshift around 8 or 10 to 10-ish. So we're interested in the astrophysics part of the cosmology, where we're hoping to use H1 to map out the history of realization and to study the property of IgM and with the first generation experiments, if we are lucky, hopefully we could learn something about the ionizing region and ionizing sources. And so this is 20 centimeter redshifted to Z of 10-ish is in the frequency range of 100 to 200 megahertz. And this is a pretty low frequency, and it's a new window that people have been trying to tackle. And so just give you an idea, the signal we're after right now, the H1 temperature fluctuation is about 2 to 20 microkelvin, while the galactic foreground and extragalactic foreground temperature, the mean temperature is about 200 Kelvin, and its spatial fluctuation is about a few Kelvin-ish. So there are a few factors down. We need to get rid of the foreground down to that level. And at lower, so another window at lower redshift, we are interested in measuring the cosmological parameters at Z of 1 to 2-ish using baryonic acoustic oscillation and also hopefully lensing. And this is a frequency range of 7 to 800 megahertz-ish. And again, we are in a similar regime where our signal is the temperature fluctuations of only ordered a few microkelvin, while the foreground is it's about a Kelvin in mean temperature, and its fluctuation at 10 microkelvin-ish. So I'll first quickly tell you about what we've been doing with the epoch realization measurement. So this is done with the GMRT in India, and so GMRT it's probably I think it's the largest radio telescope in the world right now, with the largest collecting area. It has 30 antennas, and each is 45 diameter in size. And so this is in collaboration with Weili, Jeff Peterson, and also Chris Yarata, and our Indian collaborators. So our competing experiments are the LOFA and WA paper. They are all about to come online probably later this year or next year. And but we have already collecting for a few hundred hours of data, which we are working on right now. We have built a sort of semi-custom-made software correlator to do this experiment, and we are hoping to measure the H1 pulse spectrum at redshift 9-ish. So on the scale of about 30 to 50 megaparsec in comoving space, or in angular space is about 20 to 30 Armenian scale. We're hoping to measure the H1 intensity. Sorry, we are hoping to measure the H1 pulse spectrum on those scales. And so, as you probably heard, there are many issues related with this experiment with issues of foreground and the polarized foreground. And also, the calibration is difficult, and there's ionosphere changes, and also RFI situation. So we're still working on that, but hopefully we'll have a constraint on the polarized foreground very soon. And so now back to the redshift window. So so there are many proposed BL experiments trying at this redshift, but so what we are proposing to do with the H1 is that instead of measuring the galaxies in redshift space, instead of measuring many individual galaxies in redshift space, we are trying to do is to measure the collective emission from a bunch of galaxies, and in a given spatial in a given pixel. So in a given spatial pixel and redshift pixel, there will be many emissions, H1 emissions. It could be added incoherently, so we will have root n gain by doing it this way. And so we are trying to try out this idea, this intensity mapping idea, and by first doing sort of a prototype observation using a cylinder telescope that's built at the Carnegie Mellon University. And also, we are looking at the current and the past data using the Parkes telescope. Also, we are taking data ourselves to look at this intensity mapping idea. So, what we are trying to do first is to look at very low local in the local universe, a z of 0.04. We are trying to correlate the high pass data, which is done with the Parkes telescope, which covers 2/3 of the sky, and that's the so on the left is the map of H1 in the local universe, and we try to correlate that with the 6DF data on the right. So on the right, you can see quite clearly the large-scale structure, but on the left, mostly the most obvious is the some systematic, and also that's the galaxy across, where you could see quite visibly. But the good thing about doing correlation is that you are less susceptible to systematics. And when you do the cross correlation, so on the right, is the pointer. So on the right, you can see that's the cross correlation. So we were able, so as a function of separation, the optical separation to the radial, we were able to measure the H1 and galaxy cross correlation down to a few megaparsec scale, and the correlation length is about 5 megaparsec, and the strength of the H1 intensity is about 100 microkelvin. So this is pretty encouraging. And we also looked at the autocorrelation just by doing H1 two-point function. And so again, this is the same line in here, and this is in power. So this is in temperature, this is in power. And this is the measurement from the data itself. So it seems that we are only 2 orders magnitude in power away from our signal. So which is quite encouraging. And so this idea works. So this intensity mapping idea works at low redshift. And so right now we are trying the same exercise at redshift 1-ish by looking at the deep 2 correlation of deep 2 galaxies and the data we took at the Green Band telescope. So we are looking. So the D2, we are looking at 3 separate fields of the D2 field, which is about 2 degrees by 1 degree in angular size, and covering a redshift range of 0.7 to 1.1. So basically, we're looking at a strip of galaxies in the scale, the spatial scale is about 80 megaparsec, and in redshift is about 1,000, about 1 gigaparsec, and so this is a very preliminary result. We have we think we are seeing a cross correlation between the deep 2 galaxies and the H1 at the 300 microkelvin level, at the mean redshift of 0.9. But this is a very initial result. We are still working on it. So for the future, we are hoping. This picture shows the cylinder telescope, that the cylinder prototype that Jeff and Kelvin Bandura are building in Pittsburgh. And so there's a collaboration in working right now. It's called Chang, which stands for Canadian Hydrogen Intensity Mapping Experiment, and which aims to measure this BL intensity mapping. And the forecast, the constraint on the parameters of W and W prime seems pretty promising. You probably can read, but it's pretty comparable to the Dark Energy Task Force stage 2 and 3. The figure of merit is pretty similar to those. And so, yeah, I'll stop there. Sorry. So, and then Tingting will tell us about the H1 lensing. Right? No.
For those who don't know me, I'm Tingting. I'm a graduate student at CITA, and I'm working with Willy for my PhD. Today I will give a very short introduction on the 21 linear line works we've been working on. Most of the lensing sources people are interested in is galaxies, but there are also alternative sources such as cosmic H1 gas or CMB, I guess. Kendrick will talk about this afternoon. Why we are interested in 21 linear line as lensing sources? First, because there are experiments. There are basically, I will talk about two kinds of 21 linear line sources of lensing. One is the 21 linear line emission from the epoch of realization, which is between redshift 7 to redshift 30. And there are a few ongoing and upcoming experiments, such as GMRT, Willy and Tzu-Ching are working on, and a few others. And also, there are, Tzu-Ching just mentioned, there are also proposals to observe the neutral hydrogen at the redshift, at the lower redshift, such as redshift 1 to 3. And basically, they are proposed to use it for baryon acoustic oscillation, but also you could try to use it as a lensing sources. 21 linear is ideal lensing sources. Reason is it's the high redshift, and there are structures at the smaller scales. The surface density of the sources is very high too. It's like there are about 10 to 18 millihalos on the full sky. The most important property of 21 linear is it contains the 3D information laterally, because you know what's the intrinsic wavelength of 21 linear line. So you can measure the redshift without errors. We know for any kind of experiment, the error bars is usually proportional to the number of the project, the number of objects you measured. So Willy have argued in his earlier paper, one could measure the lensing using 21 linear line with almost infinity information, because there are so many millihalos. Is that true? We will need to test with it. This map is a simulation from Elian et al. here x is some kind of quantity defined to represent the ionization fraction, and x-axis is the frequency or redshift. First, I will talk a little bit about our reconstruction method. 21 centimeter line is a different source from CMB and galaxies. CMB is a 2D diffusive background and it's Gaussian. So basically, you could construct lensing using the two-point function of the temperature field or polarization field. And Hu and Okamoto has derived the optimal quadratic estimator in 2002. Another type of sources is galaxies. Because galaxies are resolved sources, you could measure lensing by measure the shape of the galaxies. But 21 centimeter line is different. It's a 3D sources and it's diffuse. Most importantly, it's non-Gaussian. Some group of people have tried to construct optimal estimators for 21 centimeter line lensing. Some people start from the approach quite similar to CMB. They derive the estimator in Gaussian assumption. For example, Dan and Zanariaga generalized the 2D CMB lensing estimator to the 3D case. We will call it optimal quadratic deflection estimator later. We start from that approach because kappa and gamma have different Lang-Gaussian entities. So why don't we derive them separately and calculate with the combined estimator? Because we could measure the noise for each separately, then we could have a better estimator for at least for Lang-Gaussian sources. Other groups also derived kappa estimators such as Metcalf and White in 2007. Their estimator is a 2D estimator and is not optimal. We found all these estimators are basically a covariance of two smooth temperature fields. Here, TW1, TW2 are the smooth temperature field. And we found the optimal window function. The product of the two window functions is proportional to the gradient of the power spectrum of sources by kappa. Oh, by the way, this equation works for the cases when lensing varies very slowly compared with the sources. But when lensing varies fast, you need to normalize the estimator by a Bayes factor. A little bit more on the estimator. So what we learn from CMB lensing is kappa is a two-point function of the temperature field. Therefore, the power spectrum of kappa is a four-point function of the temperature field. Therefore, the variance of power spectrum is the 8-point function of temperature field. And this 8-point function is what we use to calculate the error on cosmology parameters. For 21 centimeter line, the temperature field is not Gaussian. And there are double Lang-Gaussian effect here. First is the 4-point function couldn't be calculated by 2-point function, and the 8-point function cannot be calculated from the 4-point function. Let's have a look at the power spectrum itself. The power spectrum came from two parts. One is from the lens itself, another part is from the noise. And the Fisher matrix also comes from the two contributions. When we try to solve the optimal kappa estimator, the way to do it is to minimize the noise of kappa, that is CR noise. And we found a very interesting result. Though T is not Gaussian here, and therefore, you couldn't use you couldn't calculate the 8-point function from 4-point and 4-point from 2-point. But numerically, we found the Fisher matrix of CR is diagonal. Therefore, the 8-point function becomes somehow Gaussian again. Then we applied the estimator to a simulated source, and we did a test with different sources and different estimators. First, the source we used from simulations are generated by the dark matter distribution in n-body simulations. We assume the neutral hydrogen follows total gas, and the gas follows dark matter. So basically, we are investigating the Gaussianity introduced by the nonlinearity of gravity here. And we have the Gaussian sources. Then we try to generate Gaussian sources, which has exactly the same power spectrum as those non-Gaussian sources. So we can test how much non-Gaussianity affects our result. And we found for the Gaussian sources, our combined estimator has the same signal-to-noise ratio as the optimal quadratic estimator. Let's look at this plot. The blue curve is the noise of it's the noise reconstruction noise power spectrum from the Gaussian sources, and we found the Gaussianity of sources increased the noise by orders of magnitude, which is, for example, the red curve is the non-Gaussian noise. You could see there are about there are about 2 orders of magnitude difference between them. And we found our combined estimator has better signal-to-noise ratio than the optimal quadratic estimator. To compare with the cosmic shear surveys such as galaxies, we also plotted the galaxy shear noise from a cosmic shear survey with number density equal to 40 galaxies per arc minute. And we found the 21 million lines competitive with the cosmic shear survey. And for the 21 million line lengthening, the signal-to-noise ratio is better than 1 for L smaller than 6,000. Okay, we have talked about the optimal Gaussian estimator in the past few slides, and actually we are also trying to develop an optimal non-Gaussian estimator. And we found the optimal non-Gaussian estimator can be calculated by using the Fisher matrix of the sources. So basically, you couldn't calculate it analytically, but you could, if you have the source distribution, you could measure it numerically. And similar to the Gaussian sources, if the fluctuation of kappa is lower than 1 over k, then you have this relationship. When kappa fluctuates faster, you have to deconvolve by a Bell's factor. And as Lan Hui has talked about the distortion of the correlation function of galaxies on Wednesday, actually we are talking about something very similar here. The power spectrum of the 21 million line is also distorted by lensing. And kappa is basically proportional to the change or the distortion of the power spectrum divided by some gradient. Here, G is the gradient of kappa, approximate of kappa. We found the optimal estimator, which could minimize the noise of kappa, is like this. And the product of the window function is proportional to the sum of the inverse matrix of n times the gradient term. Here, n is the Fisher matrix of the source power spectrum. When the source is Gaussian, n could be calculated analytically. It's basically proportional to 2p squared. And with this relationship, we came back to the optimal Gaussian estimator. And we try to apply the non-Gaussian optimal estimator to sources at a lower redshift. The reason we try to work with the low redshift neutral hydrogen gas is because it's closer, therefore there's better possibility to be detected. But the problem is the Lang-Gaussianity is more serious, so we have to apply the Lang-Gaussian estimator instead. And we try to reconstruct CITA with the optimal Lang-Gaussian estimator with neutral hydrogen at redshift 1. Okay, here's the plot. We found Lang-Gaussianity is even a more serious issue here. The triangle is the reconstruction noise of kappa of the Lang-Gaussian sources, and the white dotted line is the reconstruction noise for Gaussian cases. Also, I forgot to mention, because in experiments, the experimental noise are usually an exponential function of scales. Here we simply assume you could simplify the experimental noise by a hard cutoff of the scale. So for example, in this plot, Air max means the cutoff scale of any experiment. So basically you could calculate the variance of kappa, the dependent of variance of kappa on the experimental scale you try to explore. And actually, a very interesting thing is here is the noise of kappa drops and then it goes flat and it drops again. So basically, if you try to do experiment at this region, you don't really gain much. And the vertical line is basically is the experimental noise from the singular telescope Tzu-Ching just described. Okay, it's concluded. The nonlinearity or Lang-Gaussianity makes life more complicated. And experiment with less noise sometimes does not really help. The precision of power spectrum is increased with large area, but not necessarily with higher area. And for survey strategy for neutral hydrogen, wide is better than deep. We present a lensing result with neutral hydrogen and found the information from cosmic H1 lensing is not in fact due to Lang-Gaussianity of gas, but still competitive with galaxies. Okay, so we are still working in progress. Well, we are trying to work on the tomography of the cosmic shell with the 21 centimeter line, and we try to calculate the CR from different redshift beams and try to calculate the coarse power spectrum. Therefore, we could have the coarse Fisher matrix. Then we try to constrain W and W prime from the 21 centimeter lensing. And one will be interested to know if there is also information saturation effect in W and W prime. And Olivia is working hard on this now. Okay, so that's my talk.
Unfortunately, I haven't been able to get my technology to work to transfer my thing onto the Mac, so let me see if the transferring the cable works. Okay, so the next step that I want to take is to ask the question of how accurately you can actually measure lensing power spectra. Okay, and that's a problem that actually got motivated by the previous exercise when we started measuring the amount of information, the fidelity of the reconstruction of diffuse sources. The results that Tingting found is that if you use large-scale structure as a lensing source, then having more modes or having a higher resolution on your large-scale structure map does not, in fact, allow you to reconstruct the dark matter map any more accurately. So in the microwave background, if you had a Gaussian field, the reconstruction should go as the number of modes whereas what we found is that there was a saturation. Well, we weren't the first one to found that, and that as well you don't do as well as you would like with a finite with a nonlinear clustered source. Well, that clearly is not good news for somebody trying to reconstruct lensing. But we turned the question around and we said, well, if you've got a problem understanding your sources, does that same problem apply to the lenses themselves? Okay, so does because lensing, most of the sensitivity, most of your modes come from a nonlinear regime of the large-scale structure, and the question immediately arises: how accurately can you actually measure lensing power spectra and therefore derive cosmological parameters? Now, one of the naive expectation that you would like is that as you go to to smaller angular scales by increasing the number of galaxy density, for example, that you improve your variance on your signal by 1 over L squared, or 1 over N in case of the number density of galaxies. However, there's been work in recent years, I think driven by Ryan and Hamilton, that the amount of information contained in a power spectrum does not increase in a translinear regime. Okay, so that this formula that doesn't hold in a certain regime of L's. And lensing, of course, is just about measuring the dark matter power spectrum. So if the dark matter power spectrum doesn't contain information, it might be difficult to extract cosmological information out of the dark matter power spectrum. So the premise needs to be checked. There have been studies of this. This is not, of course, a new idea. Hu and White in 2001 measured the covariance matrix of the power spectrum, and so did Zimboli et al. More recently. And the general impression one gets from the papers is that the effect in any regime that is probed by current or future surveys is modest, no more than a factor of 2 in the even on small angular scales for the parameters that people had talked about, which seems at odds with Tingting's plot, where you saw a 2 order of magnitude change of information. Okay, a factor of 2, a factor of 20 does matter at some point. So let's look at what the current story is about how much information is there in the dark matter power spectrum. Ryan and Hamilton asked a fairly simple question of how well can you measure the amplitude of a power spectrum. So forget about something complicated, just the zeroth order question. How accurately can you measure, let's say, sigma 8? This would be the, I think, the equivalent of just varying sigma 8 and nothing else, keeping everything else fixed. How well will we do on essentially sigma 8 in the way that they parameterize this particular plot? And there again you go and in a simulation you measure the power spectrum, and normally this dotted line that says a count number of modes. Okay, so the information should go as number of modes cubed, or that's one of the variants on your error. So this is how this should increase with increasing resolution or increasing modes that you measure. Well, what they found, much to their surprise, or to everybody's surprise, I think, or perhaps not, some people may have anticipated this, is that the information in the translinear regime does not increase. Okay, this is very strange. It says that if I've measured my power spectrum at a k of 0.2, there's no need to measure it at a k of 1. It's the same. Okay, so there's no need for me to have done this high resolution survey. And that seems very strange, but that's the result they got out of their simulation that's been checked meanwhile by other groups, including Mark Nyrink and Sapuli and others, that the amount of information contained in the dark matter power spectrum saturates in the translinear regime of a k of 0.2 or so. Okay. If you translate this k of 0.2 into an angular scale for a typical lensing metric of 0.5, this L is 300. Okay, and out of 300, that's like, a quarter degree or something, half a degree, below which there's no more information in the dark matter. Yes, Gary?
This is just a measurement from the 3D, the information in the 3D power spectrum, right? You're not counting the information that comes from all the distances that are built into the lensing projection.
This does not. This is just asking how well can you measure anything, and then you can ask, well, at any given redshift, I can only measure the dark matter and power spectrum to an accuracy of whatever, let's say 10%. Of course, you can do that 2 different redshifts, each one of which you can ask how accurately could you have measured it. I mean, forget about lensing. Imagine that somebody gave you a simulation and you could look at each redshift separately. Right? What you would do is you would say, okay, measure the amplitude here, amplitude there. How well have I measured it? I'm going to subtract them, and that's what
but
you would
there's
do.
something else you measure in tomography, which is the ratio of the power in each mode.
As at a fixed lens plane, as you vary these source planes, that's what Bubenish has been, it's related to what the things that Bubenish and company had been doing for a while. And that's purely geometric. So they have all the purely geometric and lens-lens correlation things that one can measure, which are unrelated to this effect. Okay? So there are some things that are purely geometric, and Bubenish I think they didn't mention much about that today, but certainly has given other talks and has
This is
papers on that.
You can learn about sigma 8. It's not. It says those that K range doesn't help you learn about sigma 8, but it's not true that the corresponding L range doesn't help you learn about dark energy, right? There's all the geometric information in that L range.
Yes, even though, again, there's disagreement in the literature. So, for example, Bubinish, in his estimates, that amount of purely geometric information is actually fairly difficult to extract. Maybe Bubinish can comment on that.
It is, but Gary's talking about something broader, not just cross correlations.
Is
There's a paper by Ujan and Molinox and Tice and Tony just last week saying the distance information actually carries more of the dark energy. The distance measurement part of the geometric part carries more of the dark energy information than the part where you're investigating the amplitude of the power spectrum.
Well, I mean, again, there's the same as the Chang and Hui analysis a few months ago. So what they say is that they try to project it into a geometric and into a dynamical component, right? So one is you can ask how does the power spectrum evolve with redshift? That also depends on dark matter. And the other one is how geometric distances change in a couple of different respects. One is shifting scales of the power spectrum, and the other one is just changing the purely geometric ratio of distances. Now, again, I think this is a very technical question that needs to be addressed in terms of a...
But just to understand, this plot refers to one of those three kinds of information.
Yes, I'll get to the information that we actually want. I don't actually have an answer to what actually happens, but let's take a look at how calculations actually are done. Okay, so what goes into how well you do on any given survey is you have to specify not just the power spectrum, but the covariance of your power spectrum between two L bins. Okay, and that gets propagated. In the end of the day, you have to propagate that to get the error on whatever you're going to estimate at the end of the day. So if that's the prescription you start with, then how Ramsden and Hamilton explain their result qualitatively is that once you cross the nonlinear scale of about 0.2, that the modes become highly coupled, and that to measure the structure of dark matter, now you have to be careful what this means. This is a power spectrum, not the structure of dark matter. Dark matter, of course, does not look the same at different scales, but that the additional modes don't actually tell you anything new about the power spectrum. And they find that there's a saturated mode covariance at high L, which seems very surprising, which says that as far as power spectrum measurement goes, you could have stopped at small l, and there's no information to be gained going to higher L. Now, let's look at this in a lensing context, and we did the same.
You're not emphasizing the fact that this is totally related to the box lengths. Like, for example, I mean, the 256 is doing much better than the 128 box size, right?
Not when you rescale it. In the previous plot, they claim there's no box dependence, right? Well, the two box sizes lie almost top of each other, certainly over here. At low redshift, of course, the nonlinear scale enters the horizon side, and the nonlinear scale is no longer tiny compared to the box size. The small box size gets to be small. But certainly in the regimes where that doesn't matter, the two circles are the two different box sizes. So when you translate it into information, and redshift of 1 is actually no different, and redshift 0, the boxes differ a bit, and that they think is due to just the small box is a bit too small. Scaled by the volume of the volume, scaled relative to the volumes. Yes, information does increase as you have more volume, but the saturation still occurs at the same L. That's what they claim. This one. Next one. Yeah, the x-axis is different. You have to shift. You have to cut out. If you cut out this regime, then these two look. Well, the whole thing is different. So you have to shift these two plots. I should have cut out one. I guess would have been made life a little bit easier to shift.
I mean, I thought the impact that these guys in Roman talk about is related to this heat coupling.
That's right. They explain this. They explain this as coming from this is an interpretation of why this is, and they look into all the configurations that go into it. But at the end of the day, this is all that really matters as far as information goes and propagation of errors goes. That's the only number which you really need to propagate. Right?
What do you mean by information?
Okay, I'll get to that in a minute. And the next in the slide after this, I will. I guess I'm running out of time. But let's just first ask a question that there are a few parameters that need to be checked first. First of all, that was a three-dimensional dark matter power spectrum. It does not immediately follow that the two-dimensional power spectrum has the exact same property. So that's the first thing you need to check. And here we find, what we do is, the information as a function of the projected kappa maps. You can do the exact same thing. Instead of doing measure in 3D, you measure it in 2D projection and measure the power spectrum in 2 dimensions. And you want the exact same algorithm on a 2D projected stacked kappa map for some fixed source redshift. And actually, then of course depends on, your stack and recycle simulations. You wonder, your answer might depend on how many simulations went into your stack and whether recycling and things like that matter. It does matter somewhat, so the most we've been able to push through so far is 22 independent n-body simulations from which we sample the slices to stack to do this. And again, at about the scales that you would have just naively interpreted from Williams and Hamilton, L of a few hundred, 1,000, you again see, information drops, saturates, and then again turns down. This plot is upside down from the Williams and Hamilton one, but it's the same general qualitative phenomenon that the information shows a plateau.
Is this also information on sigma 8?
This is information on the amplitude, which is parameterized, keeping caveats, everything else fixed, etc., etc.
The amplitude of the CL.
The amplitude of the CL, yes. This is the information on the amplitude of the CL.
Holding cosmology.
Holding, well, here's not even the cosmology. For this exercise, okay, I mean, this is all of simulations the same cosmological parameters, so we didn't actually vary. So if you want to differentiate the nonlinear to linear power spectrum, the linear things have additional things in there. That Williams and Hamilton, for example, this is purely linear. The transfer function itself has deviations. There are some complications to it, but this is just takes the trace of the covariance matrix basically and just says how well can you predict a higher order mode from a lower order mode. That's all you're saying. If I stop my CL over here, can I predict my next CL over? And the answer is yes. Okay, that's.
You predict the higher order power from the lower order power.
Yes, that's what it says exactly. So if I only plot at this point in my CL, I can tell you what the next point is. That's what this plot tells you. And again, if you plot the same cross correlation, you find it looks pretty much the same in projection. So this 2 to 3D is not qualitatively any different, and you get the same information saturation in this translinear plateau. That the modes couple strongly. You need to, any one mode will tell you what the other modes are doing. There's no need to measure the CL at the different L's. Well, even sigma 8 is fixed. So this is just the covariance. Again, this is something very simple. I just have 60 kappa maps and measure the power spectrum on each, and then I tell you, I give you a measurement of a CL at 1L. I say, if all I do is linear except if I just take the mean and the covariance of those CLs, everything is the same. Sigma 8 is even the same for this purpose. This just tells you how well can I predict a different L from a lower L. And if they're correlated, that means if you just show me the first half of the plot, I can tell you what the second half will look like.
So this is very well-defined, I agree. So that's log of L?
The log of L against log of L, right? So that's the same as Williams and Hamilton.
There's a science duration happening at 1 or 2,000. Whereas your previous plot you said 500.
Well, like the color coding is it's by eye how much the grayscale translates into the color coding and how much, when you integrate over these colors, how much you gain. But the first point, is at an L of 1,000 and up it couples. So at an L of, again, these are very coarse bins, but this is the. Sorry? Okay, let's just go through again again, this is not the whole story, right? This is not, this is only a statement about how well can you, by measuring one L, predict another L in your CL power spectrum. And in the Gaussian case, you couldn't do anything at all. They're all completely uncorrelated outside your window function. Now let's just see how this propagates. So again, what you generally do is you have a power spectrum that depends on your favorite cosmological parameters. That's what you normally start with. And then you differentiate, you Taylor expand this about a point, differentiate it, and propagate the errors. I'm going to jump over this and just show the plot and skip my words. So what you do is you have some parameters you want to go after. Say W's, you got some power spectrum which you differentiate for these. So just, in the linear order, Fisher propagation, just talk about the simplest possible scenario. Then you say, well, I want to solve what I want to know is say W or some vector of W's, and what I measure is some observations of a power spectrum. So I subtract these two, I have the theoretical in the model, and then the W depends on some linear function of what I observe, which is a power spectrum. There's an optimal weighting to get these power spectra, which is an inverse noise weighting times these projection matrices. Okay, so this is a standard propagation of the Fisher matrix. And at the end of the day, what you care about is the error on the parameter at the end of the day. Now, the other one at the end of the day is just the propagation of the errors of the original power spectrum to start with. Okay, this is just a linear propagation through. At the end of the day, that's all that ever happens. And then the question is, the whole question hinges, if I could have scrapped all the L's above 1,000 and the answer won't change, okay, then my error calculated at 1,000 might have some relation to a higher L. That's the yes, Sarah.
So this is ignoring the shock noise that you get on the high L's.
Well, the N is supposed to include that as well. Like the N's are supposed to include both short noise and the signal intrinsic covariance.
If your shock noise limited, then this is not relevant. When you gain by having more and more observations, it's just like having many modes. It's just like if each L has got independent shock noise on it.
Yeah, but this thing, if your short noise even was 0, which you can't do better than that, your information saturates. So if you add short noise, your information goes down.
If the shock noise is non-zero, then you gain by having more observations.
Yes, so what happens is if you add short noise, then the high L's you do worse on than the pure signal matrix. And of course, as you reduce the noise, you can probe to higher and higher L, right? So it's not exactly the same, but in this cutoff, we assume the short noise basically is a delta function at some L. In reality, it's a power law. It's in fact L goes as almost exactly as L squared.
But you actually gain by probing more and more L's if your shock noise dominated, because each time you probe another L, you're beating down the shock noise.
I just think that for future survey, in this region, like at 1,000, you have short noise really low, right? So you are almost to the signal. I mean, you're almost to the signal.
For what survey?
I think for since short noise at 1,000 is very, very
Well,
small.
if you were,
How many percent?
and then still only if you're just looking at the whole projected correlation function, once you've divided it up into slices.
Then you have to ask how the L's correlate between slices. The question is, if on each slice I can predict the higher L's, does the cross correlation decohere as I go to higher? That's an unknown. We haven't actually done that yet. So before I make any more claims about this is just outlining what the first order effect is that you have to worry about. Is that I think it is what we do see is that the error in the power spectrum is strongly non-Gaussian above L of 500. I think that's a statement which just follows from these plots. What that does for other things, well, needs more work in propagation. As Tingting says, Olivier will tell us on Monday what the answer is. But the basic qualitative effect is that this three-dimensional information saturation measured by Weinberg and Hamilton seems to carry over directly to the projected dark matter, and that's perhaps not highly surprising, even though it was not seen in previous, it was not seen by Hu and White, the symbology at all. There's no way that I have of mapping their covariance. They don't publish it, two-dimensional covariance matrix of the correlation function, so I have no way of comparing our result to theirs. As pointed out, in order to say something interesting about cosmological parameters, you have to propagate this whole thing through the previous equation to actually make an intelligent statement about figure of merit, which I have not done, so I don't know what that actually ends up at the end of the day. However, we have to be careful that there are certain regimes. There are regimes in which the two-point function does not carry the information that you might naively expect from a Gaussian source. So this certainly is something that one shouldn't just ignore. Okay, I think it is fair to say that this is an effect that is not tiny, is not trivial, and is a factor of about 20 change in the just information content of a single redshift power spectrum, what Rhimes and Hamilton see. Does not mean that translates into a simple way onto anything else, but it is a large number to start with that one has to keep floating about. So this is, I think this is the level at which we currently understand this phenomenon.
So it's certainly an interesting topic, and to some extent we're seeing similar hints in analytical estimates based on following calculations of the Taylor model. I have a couple of specific comments. One is that I think you have to be careful about it. Statements like order of magnitude information loss. I think that's almost certainly wrong in many senses of information loss.
Information is defined by Rhimes and Hamilton. It's not of magnitude.
Well, you should define your own information that you can defend that's relevant to lensing studies. I mean, your covariance matrix that you showed was a well-defined quantity. And so you can make statements like at L greater than 1,000, the coefficient is bigger than 0.5. Those are pretty well-defined statements. You can also make well-defined statements about there's a degradation in measurement of W of this factor. But this particular phrase that you have doesn't make sense. The comment I had was that there's a well-defined quantity, which is the non-Gaussian covariance that you can analytically estimate. The Hiller model is certainly a good way to get it to within 30 or 40%. And that's been estimated by covariant tools. And that degrades information to less than a factor of 2 at L per 1,000. Okay, that's a quantitative statement I'm absolutely certain of. So the excess degradation that you may be getting that Rhimes and Hamilton hinted at, not hinted at, but claimed quite strongly, is related to beat coupling, which is related to the size of the box. So if you then say that you're getting this factor of 5 extra degradation and it's independent of the box size, that's just going to be wrong.
What I said, Rhimes and Hamilton find the box-independent effect, right?
Well, you tell me, do you think that you're finding an order of magnitude degradation in the limit of an all-sky survey?
Well, it depends on what senior order of magnitude. This is the Rhimes and Hamilton, the information as defined by, I didn't define this object. Rhimes and Hamilton defined a statistic, which, as I say, does not translate into anything easy by the time you get to a figure of merit or something. But they did define an object called, what they call information, okay, which is well defined relative to their definition.
A well-defined statement. At L of 1,000, the degradation in a dark energy measurement is less than a factor of 2 for an all-sky survey compared to the Gaussian case.
For W, you mean, sir?
Or, yeah.
Right, we're talking about, I guess, like sigma 8 or something.
Well, you tell me a parameter, I'll give you the quantitative statement, but it's going to be pretty close to a factor of 2. So that's my statement. And if you're saying that it's a factor of 5 worse, I'd love to bet something expensive. But I can't bet against something runs some information running.
Right, Francis?
Yeah, well, I'm not sure I understood exactly what information consideration meant, but I mean, assuming you're right that the two subsequent bins that are fully correlated, I think that is very good news. It means that I can predict if I measure one bin and the second bin, the relation between the two is going to depend on the cosmological parameters, but independent of the particular realization you are in.
Well, no. As we say, depending on the question you ask, and as Booth says, the information is relative to the definition.
Information saturation. It suggests that there's no point in going to higher F. And right.
It's not worth losing them.
And this is not good. What it suggests is that there is a kind of separation of information. And so you may be.
Look, I'm not making any claim on any information other than what Reimers and Hamilton defined. So we did a very well defined question here, which is, does the projection of 3D to 2D change the Reimers and Hamilton result? And the short answer there is no. Okay, and what it says is that that the covariance of bins is not a negligible effect. I think this statement also follows in the projected covariance of the CLs. But anything else, it also depends on the thing you're trying to measure as it be propagated through. So that's I'm not making any statement about what impact it has on any other parameter you differentiate to. But it does say that ignoring it could be a significant change from assuming Gaussian to non-Gaussian could be very different. That's all I'm saying. And that means you need to actually do the calculation of a full covariance to know the answer. I think that's all we're saying here. And I think it's hard to argue that our covariance matrices look anything like Gaussian. They don't.
Well, I mean, another way of saying, I think what Frank is saying, and what some other people are commenting, is that what you're doing is measuring your information is only about the amplitude of the power spectrum. So what happens in the nonlinear regime is because the modes are so coupled from realization to realization, all the beams go up and down together, right? So then that's very bad for measuring the amplitude, right? Because the amplitude is fluctuating, and so it's very hard to put a good error bar on the amplitude. However, it's very good for the spectral index, for example, right? Because if you have the case where all the beams are independent, measuring the spectral index is really bad. But if they are all fluctuating together, it's good. So you have to be careful, when you do.
Yes, no, I agree. As I said, yes, as I said.
People that do this for a living, I think they're doing it, right? So that's what these guys are saying. It's not me.
All right,
I propose that we close this discussion. All in favour?
I do like it.
Mike. No, I was agreeing with that. I don't make a comment.
One of the things that is going on with that, with the spectral index, is correct, but also one of the things that you want to measure is how things vary in redshift, to measure W. And in fact, the covariances between the redshift slices are large. And just like with the spectral index, it helps you to get the lever arm. Well, that actually helps you to get the lever arm on W as well.
I think all this is saying is that the Fisher propagation should be done on a full covariance matrix. That's all we're saying. We're not saying anything about the errors and anything else. We're just saying that the Fisher, assuming to be Gaussian, could be very far off from what it really looks like.
Nobody's using a Gaussian covariance matrix for that.
A lot of people do.
They should be usual. I can help.
All right, one last question. Joaquin?
Okay. Obviously, I'm not in the field. Yeah, but
Joaquin, last question.
okay, then
I understand conceptually that the alignment of the modes between modes will destroy information in that closed plateau, but why is it going up afterwards? Is it a feature of how you define information, or there really is a doubling of the free mode, and why is it going up afterwards?
Oh, the why, I think, is a much deeper question than the what. So again, there are people who write papers on that, and that I think is beyond what I can answer easily in the next 10 seconds. But I'm certainly happy to talk about what other people think.
All right, so let's talk about lunch. So let's thank Tzu-Ching, Tingting, and Maria. And we'll start at